Hey everyone, and welcome to the first video in a new topic. So for the next two lectures, we're going to be looking at the p-block elements and their compounds and the way they react and everything really. And this time we're going to do about 8 videos. So this time, the first one will be just taking an overview, looking at the sort of chemistry that governs it and a lot of the periodicity. And then we'll have 6 videos, each of them looking at a group from 13 to 18. And then finally, there'll be a summary video because this time, unlike with the S block where group 1 and group 2, there's some really obvious trends and we could talk about the whole group really easily. As you'll see, even from this first video, the chemistry of the P block differs tremendously from each, even in each group, because you'll have metals and non-metals and metalloids in the same group. So what we'll be focusing on this time is how things like oxidation state and something called the inert pair effect that we'll be looking at come into play and dictate the chemistry involved. So I'll talk about them in this first video, but then I'll summarize and give another focus on them in the 8th video, the last video of this block as well. So let's start by just looking at some generalities before we start. So as I said, the P block, the pure elements, they're there as metals, metalloids and non-metals, so the whole spectrum. And this is dictated by the ionization energy, which we'll be talking about in a few slides. When we're looking at compounds, we'll be looking at things like the oxidation states, which are governed by the valence electrons and the inert pair effect. We'll focus on that a lot because that dictates most of the chemistry. And we'll see a few trends in there as well. The nature of bonds changes a lot in the group as well as between the groups, and this again is due to electronegativity. So we'll be using that the Van Artel-Ketelaar triangle again to predict ionic, metallic, covalent bonding. And bond enthalpies change a lot. This is due to the electronegativity and the atomic radii. And we're going to be looking at trends in atomic radii in a bit more detail in a few slides. And then finally, the reactions of some of them. So we've got a lot more Lewis acid, Lewis base reactivity happening. We touched on it a little bit in the hydrogen lectures with the boron hydrides, boranes. And this is due to electronegativity and things like electron deficiency as well. So let's start by taking a look at some P block elements. This isn't the whole P block. You'll notice there's quite a few of them missing, including whole periods. But yeah, this is just how diverse they can be. So I mean, we've got carbon up here, which we've already looked at a lot. It could be graphite like in your pencil, or beautiful diamonds like here. We've got nitrogen and oxygen, especially is interesting. It becomes a liquid at minus 183 degrees Celsius, and quite an explosive liquid at that. Something you have to be aware of in the lab, because liquid oxygen is actually a warmer temperature than liquid nitrogen, and we use a lot of liquid nitrogen in the lab, so you don't want to liquefy any oxygen or you might have an accident on your hand. There's fluorine, which is incredibly reactive. It will just react with most things. And right next to it, neon, which is the polar opposite, will not react with many things. Although we will actually be looking at the noble gases in one lecture and how they do make some compounds. And then we've got some poisonous elements, some that melt, one that is actually at room temperature, a liquid, which is very rare in the periodic table. And then even radon, which is a gas that's radioactive. So it's a super diverse block of the elements, and we'll be looking at it piece by piece. So let's take a look at the P block as a whole and go through some of these generalities and trends and periodicity. So it's called the P block because the valence electrons are in the P orbital. So you'll either have 1 to 6 valence electrons in this P orbital. As I was saying, the chemistry is a bit more complex than the S block. It can change quite a lot, and that's because we've got all sorts of different elements. So instead of them all being metals like we saw with the S block, this time the P block's got metals, which are shown here in red, metalloids, sometimes called semi-metals in purple, and then non-metals in green. And this is really dictated by the ionization energy. So I think it was the very first video even, we were saying that things with a low ionization energy tend to have metallic bonding, tend to be metals because they can easily become cationic and have these this electron pool in the metallic structure. So I've put the arrows here showing which way electron ionization energy increases. So that's why we've got non-metals at the top right part because they've got high ionization energies. But in the bottom left here, where the ionization energies are going to be the lowest, that's where we find the metals. And the P blockers split it into families. So some of them have fancy names, some of them have very uncreative names. So you've got the boron family, group 13, the carbon family for group 14, the nitrogen family for group 15. Group 16 is called the oxygen family usually these days. It can also be called the chalcogons, but this is quite an old-fashioned name for it. And then we've got the halogens, group 17, still called it, and the noble gases, group 18. And we'll be going through these in the next 6 videos one by one. And on this slide, we're going to see how electronegativity plays a big role in the P block. So the compounds of the P block elements, we get a wide range of structural types, literally everything we talked about in the second lecture on solid structures. We can get ionic lattices, covalent network structures, and discrete molecules with covalent bonds. Obviously, this is dependent on the electronegativity of both of the atoms involved. For covalently bonded compounds, the bonds will be polar, and this also depends on the electronegativity. So you've got partial charges, such as the delta plus on the less electronegative atom, and delta minus on the more electronegative atom, and this impacts reactivity of the compounds a lot. And then finally, something we'll be looking at and really focusing on, as I've said already in this video actually, is the oxidation state. And this, we have to take into account electronegativity. So for example, I've got an example here of nitrogen NX3 compound, say, and if it's making nitrogen trifluoride, the oxidation state of the nitrogen is +3 because the fluorine is more electronegative. Whereas if you make ammonia, sort of the same formula with hydrogen instead of fluorine, then the nitrogen is the -3 oxidation state because the nitrogen is more electronegative. So this, plays a big role in the chemistry. I hope you're familiar with calculating oxidation states. We've touched on it briefly, looking at the hydrogen and the S block and that. But if you need more information, there are like a set of 10 rules. I'll go into it in more detail in the final video when we're summarizing. But I've made a help sheet and that's already on Blackboard. So I'll, I think it's one side of A4. I'd encourage you to read that. It's like, this is my best explanation of it, I think. And how to calculate the oxidation states for each of them. But in this table down here, I've got the most common oxidation states for each of the groups, and you'll see some trends already. Like the oxidation state is related to the group number, especially if you take 10 off it. Pretend the transition metals don't exist and call them group 3, 4, 5, 6, and 7. The oxidation state generally follows that, and then you'll get one that's 2 different. And we'll go into the reason for that when we're talking about the inert pair effect. So here I've got some examples of the most common oxidation states for each of the elements. So in blue is the oxidation state of the oxides, and in red is the oxidation state of the halides. And there are already some trends. So for the third period and lower, so that's from this bottom part here, from aluminium, silicon, and that down, you'll see that the maximum oxidation state increases from left to right. So here it's 3, 4, 5, and then we can even get to 7 in the halogens. 8 if you go to xenon, but that's not so common. But the second period, this doesn't happen, and there's a couple of reasons for that. The first is that we can't do the octet expansion. If you remember back to the first lecture when we were talking about Lewis structures, some of them can have more than 8 valence electrons. That's necessary to get some of these really big oxidation states. And also the high electronegativity restricts the oxidation states. So you can see that fluorine is only ever -1. And that's because there's nothing more electronegative than fluorine, so it's always going to have the negative oxidation state and have the electrons. Likewise, oxygen is the second most electronegative. So I mean, if you want to find oxygen in this -2 oxidation state, it's going to have to be bonded to fluorine. So let's start looking at the periodicity of P block compounds and trends we can see. So the first one's going to be looking at the structure and bonding of oxides and halides. and how this changes going across periods. So metals, which you'll remember are sort of on the left, the bottom left of the P block, because they've got a lower ionization energy, they tend to form oxides and halides with extended structures with high degree of ionic character. So this is very much like we saw for the S block metals, actually. And I've got some P blocks down here that show the structures of P block oxides and fluorides, and you can see that these are yellow ones with the metals, ionic structures with some covalent character. And the metals form with the fluorides and oxides. Both of them are ionic structures with some covalent character. As we go across a period, the difference in electronegativity between that P block element and the oxygen or the halogen decreases. So then the ionic character also decreases, and the bond will become more covalent. And so we can see this going across, this group's a good example with gallium, germanium over to a bromine of the oxides. It starts with an ionic structure with some covalent network, some covalent character. Then we get to the covalent network structures, and then finally we have discrete covalent molecules. And the same happens with the P block fluorides, but they're more often discrete covalent molecules, but you see they start as ionic ones, and we've even got a few of those covalent network structures. Now let's look at the oxides in a little bit more detail, and specifically the acidity and basicity of them. So this also changes as we go across a period. So the non-metal oxides, which are the ones in the top left, top right even, sorry, here, these tend to be acidic, and they'll react with water to form acidic solutions. They're highlighted in red in this periodic table over here, or periodic P block, should we say. And then as we go towards the metals, they become amphoteric. And this does line up, not perfectly, but quite well with metals versus metalloids and non-metals. So the non-metal oxides are acidic. The metalloid oxides, and some of the metal oxides as well, aluminium, forms alumina, they're amphoteric, which means they'll react with both acid and alkali. And this is something we saw with beryllium oxide as well. And you'll actually notice that if we put the S block here, it does join in with the pattern quite nicely. Because finally we've got oxides of electropositive metals, which we saw mainly in the S block, are basic, and they'll dissolve in water to form alkaline solutions. See, if you put the S block here as well, there'd be a lot more green, so there aren't too many of these electropositive metal oxides in the P block, but the majority of the S block would be green, apart from beryllium oxide, which had the amphoteric ones, that'll be a purple up here. So it follows a trend, like across a period, as the electronegativity goes up, things become less metal, more non-metal, and then the oxides of these elements go from basic to acidic. Next, we're going to be looking at a few trends in periodicity going down the groups rather than across the periods. And the main differences we'll see are between the second and third period. So the second period being the top row, which is always, even after all these years, something that takes me a second to realise, because we'd have a helium up here, and hydrogen just in the middle of the periodic table, counting as the first period. So the largest differences are between the second and third, which are shown here. And this is mainly due to the fact that this is where a big difference in the atomic radii happens. So if we look at the oxygen group I've highlighted here, the increase in atomic radius from oxygen to sulfur goes up 40%. And it's a similar very large increase when we look at the anion size as well. But then when we go from sulfur to selenium, so from the third to the fourth period, it's only a 14% increase in atomic radius, and a similarly small one for the anionic radius to increase as well. And then we see again from the fourth to the fifth, it's not such a large increase as well. And the reason that there's a big difference between the second and third period, but not between the subsequent ones, or not such a big one, is because of the D block elements. So these are between calcium and gallium in the fourth period. And I've highlighted them here. It's like a thick green line to show this is where we've contracted the periodic table. And why this is that the d orbitals have a poor shielding effect. So the effective nuclear charge increases quite a lot. What this means is that as we're going across, they've got a poor shielding effect, so we're adding more protons to the nucleus, but the extra electrons going in these d orbitals aren't really offsetting it. So you've got a high effective nuclear charge, and as we saw in the first video, this causes smaller atomic radius. And because the shielding isn't present in these, like the top ones here, isn't so much, that's why we get big changes. Also going down the group, we see that the metallic character increases. So we've already touched on this, so I won't spend too much time. But generally the ionization energy decreases down the group. This is because the valence electron is further from the nucleus, so it's much easier to remove. And the metallic character is directly related to the ionization energy. So the ionization energy decreases down the group, and the metallic character increases down the group. And the perfect example that I've highlighted here, group 14, carbon's a non-metal, silicon and germanium are metalloids or semi-metals, they used to be called, and then tin and lead are metals. And now let's have a look at how the oxidation states change as we go down the group. And this is one of the most important things we'll look at. So this I'll summarise in the summary lecture as well. And it's where the inert pair effect comes in. So what this is that the stability of a lower oxidation state increases as we go down a group, and it's a lower oxidation state that's 2 lower than the max. This is only holds for group 13 to 15. So we've got an example here, like lead is more common in the 2+ oxidation state than the 4, and this is at the bottom of group 14. If we take carbon, for example, which is at the top of group 14, that's more common in the +4 oxidation state. And this happens for 13, 14 and 15, as I was saying. And this is because the lower oxidation state has this electronic configuration NS2, and they're not used. These 2 valence electrons aren't used in the bonding. So these are, in effect, the inert pair. And we'll see that when I change slides to the next one. And why they're not used is because the bond enthalpies decrease down the group. And this will make, when I change to the next slide, we'll go through it and it'll make it a lot clearer. But essentially, as the bond enthalpy decreases down a group, the stability of the +2 oxidation state increases, and we get this NS2, MP2 for the group 14. So here's what I was saying. Let's look at the explanation using this figure that I've actually taken from the first lecture. So when we were looking at the valence bond theory, we looked at this, and this is an example for carbon, which is group 14. But this can be adapted for group 13, 15, going down the group as well. Let's quickly recap what happens when we're doing orbital hybridization. So in the ground state carbon, we've got 2 2s2 electrons and 2 2p electrons, and they combine in these sp3 hybridized orbitals, and then they're all used for bonding. So for example, if we've got a hydrogen, we can bond to 4 hydrogens, and they'll all use these 4. However, what we said is that this takes it takes energy to promote an electron into this 2p, but that's more than made up for when a compound is made, which is essentially the bond enthalpy is what makes up this promotional energy. However, if we're going down the group, say for lead now, we said that the bond enthalpies are lower at the bottom of the group, so then the bond enthalpy doesn't outweigh this energy of promotion, so it's not going to happen. So then for lead, for example, not that lead hydride really exists, but it works on the last example. If that was to bind with hydrogen, this promotional energy isn't made up for, it doesn't sp3 hybridize, and we just end up with 2 here. So that's essentially how the inert pair effect works and how it's related to the bond enthalpy, and that's why the lower oxidation state increases as we go down the group. So now looking at the group 16 and 17, so this is where the inert pair effect doesn't happen. The maximum oxidation state isn't shown at the top of the group, so oxygen and fluorine. This is because they've got really high ionization energies and really high electronegativity. So get into +6 and +7 just isn't possible. We've seen with fluorine even that only -1 is possible because it's got such a high electronegativity. Notice we descend the group. For these two groups, the maximum oxidation state is easier to obtain, and this is because the ionization energies and the electronegativities decrease. And finally, let's look at what happens to the trend in bond enthalpy as we go down the group. So we've just touched on it with the inert pair effect, that as we go down the group, bond enthalpies decrease. So if you have a bond, say AX, oh, there we go, pointer, AX, where A is a p-block element and X is a non-metal, so something like hydrogen, oxygen, fluorine, chlorine, the bond enthalpy will generally decrease down a group. And this is because there's poor overlap between orbitals. So as we go down the group, A will get larger, and because this atomic radius gets larger, there'll be poorer overlap between the orbitals, and it will make for a weaker bond, a lower bond enthalpy. Now the trend will be generally smooth if there's no lone pairs on X. So let's say if this was group 14, so we start with a carbon-hydrogen bond, and carrying on that example, and as we go down, carbon-hydrogen will be stronger than silicon-hydrogen, which will be stronger than going down in a linear trend. However, if there are lone pairs on X, so keeping up the group 14 example, and we're using chlorine, the first element is generally lower than the second one. So whereas for hydrogen, we said it would be CH is higher than SiH, germanium H. This isn't true if there are lone pairs on the other thing, like chlorine has lots of lone pairs. So in this case, the second one will be higher than the first, and then it will decrease linearly. And why is this? Why is the silicon chlorine bond stronger than the carbon chlorine? So this is mainly due, or in part due, to the fact that there's electron-electron repulsion between electron pairs on the two atoms. So in the example without lone pairs, CH bonds, for example, the only electrons are between the carbon and the hydrogen. So this is why it needs to be with lone pairs on the chlorine, for example. So atoms have to be close together to ensure a good orbital overlap. And where carbon's smaller than silicon, the atoms are going to be closer together. So the lone pair on the chlorine is going to be repelling the electrons around carbon. And this is greater in carbon than in silicon because silicon's larger, so the atoms aren't so close together, and this electron-electron repulsion is less. There's also the fact that the electronegativity of silicon is less than that of carbon. So we said as we go down a group, electronegativity decreases. Sorry, I've got no battery. So as we go down the group, electronegativity goes down. So silicon's less electronegative than carbon. And that means there's a bigger difference in the electronegativities between silicon and chlorine than carbon and chlorine. So there's a greater ionic contribution to the bonding, and ionic bonding is stronger than covalent bonding. That's why we see these ionic solids have such high melting and boiling points as well. And finally, this trend is more exaggerated when A and X both have lone pairs. So the example here is like nitrogen and fluorine. This is very weak compared to the phosphorus and fluorine. So it goes back to this electron-electron repulsion. But this time, rather than being no lone pairs on the carbon, there are lone pairs on nitrogen. So these repel the lone pairs on the fluorine a lot more and weaken the bond a lot. And finally, let's look at how the structure and bonding of these oxides, halides, and the group P block elements change as we go down a group. And so we already, on the last slide, discussed it when we were seeing about how the bond strength changes. As we go down a group, the difference in electronegativity between an element and oxygen, say, the difference gets larger. So there's a higher ionic character of the oxides. So this is an example of group 15 oxides. And we can see that NO2, which is at the top of the group, is very covalent. But as we go down the group, these are all much more towards the ionic bonding scheme, and this is because the electronegativity goes down as we go down the groups. The electronegativity difference gets larger. And we have, so this is just for the oxides, as I said, but we have a similar process for the halides. So if you were to do the group 15 halides, you'd see the same thing. So bismuth fluoride, trifluoride is an ionic solid, so that will be over here somewhere. It'll actually be even more ionic, because you'll remember that fluorine is more electronegative than oxygen, so the difference in electronegativity is even bigger. So that'll be somewhere over here. And we see bismuth trifluoride is an ionic solid, whereas nitrogen trifluoride will be down here still. It's a gas with covalently bonded molecules. So that's it for the periodicity and the trends going across periods and down groups. And now we'll be focusing for the next 6 videos on each of the groups independently and looking a bit more in depth at what sort of compounds get made and what they're used for.